film study. Acknowledge that we're gathered here tonight on the traditional lands of the Anishinaabe and Haudenosaunee peoples, and really grateful to be here on this land tonight, especially for nights like tonight where it's really clear and there is a hint of a chance that you might see the comet if it hasn't dipped below the horizon by the time we get up onto the roof. We have a really great talk tonight by Tai Withers, our very own. Tai is a master's student here at Queen's, having finished their undergraduate degree last year in spring. Tai's research is primarily around star formation, and we're going to hear a really great talk tonight about what we don't know about the largest stars. So for Drew, I'll hand you over to Tai. Thank you very much.
Thank you. Hello, everyone. Before I get started, I do want to continue a little bit of what Lauren said, noting that this open house is happening on Thanksgiving weekend. And while much of what many people, including myself, are thankful for is the ability to spend time with loved ones and celebrate together, Thanksgiving has also historically been a celebration of the harvest and the bountiful land that provides this harvest. And so as the child of settlers and immigrants, I do really want to pay attention to the fact that the land that my food is from is in many cases land that was unjustly stolen from Indigenous peoples and has been transformed from their stewardship into a colonial project. And so I'm incredibly thankful for many things today: the opportunity to speak, the meals I've had, the people I spend time with, and the ability to look at the stars, which is truly wonderful. I just also want to highlight that the opportunities that I have and that we all have in this room today, those opportunities are not universal. And that I do think it's our duty to try and make the world a better place. But with all of that said, let's start talking about the stars. And so I'm here today to talk about what we don't know about how big stars form, but what do I mean when I say big stars? Let's see if I can get that over here. So this is part of the Orion constellation. I've tipped it on its side to fit here better. If you're up here in the northern hemisphere, then the Orion constellation is a winter constellation, unless you're willing to stay up late. I didn't really understand that whole business about winter, but yeah, if you're just up really late, you can still see it. So this star here is Bellatrix. It's 8 solar masses, so 8 times the size of our sun. There's also Betelgeuse, Rigel, some others that I'm going to skip because I will totally butcher the names, and Almalan, which is the biggest one at 40 solar masses. Now, one of my favorites here is Betelgeuse down in the corner. You might have heard of Betelgeuse, famous for not going supernova yet, much to my great disappointment. But don't worry, I have a plan. So who here has seen the movie Beetlejuice? Anyone? Okay, yeah, a few people. So if you say his name 3 times, he appears. So surely there's some kind of way that we can make this work. Unfortunately, there is a little bit of flaw in the plan, which is that Betelgeuse is several hundred light years away. So if we made it go supernova now, we wouldn't actually see it. Our grandchildren's grandchildren probably wouldn't see it. But if anyone here does happen to have a time machine that I can borrow, do hit me up after the talk, or before or during. You've got a time machine. So given that all of those stars in Orion are so much more massive than our sun, is the sun just tiny? Do we have a little baby star that we're going around? And the answer is not really. We're actually around a pretty average star. In fact, we can make a graph of how many stars exist at various different sizes, with horizontal being how big your star is, and the vertical being how many stars you've got. And as far as we know, that graph looks a little bit like this. Exactly how all the angles work out is a really big question and the subject of quite a lot of debate. But we know the overall shape looks like this. And on this graph, we'd be about here. So we're pretty reasonable. And what we call the division between massive, really big, and regular stars is somewhere around there, so a little bit past the sun. So on the left side of the graph, we have many stars that are around the size of our sun, a little bit bigger, somewhat smaller. And on the right side of the graph, we have the truly giants. Now you might be wondering why that line is where it is. And this is one of those lines that scientists just kind of slap on a graph and say, well, it's about right there. And while there is different stuff that happens on this side and on that side, exactly where that line is, it's a little confusing. The universe doesn't like to make clear boxes for us to put stuff in, so we just have to try really hard to put lines down, even though it doesn't like it. And it does get extra difficult because we're talking about things, we measure them in solar masses. The universe does not measure things in solar masses, but we do because it's really convenient. So just keep in mind that during this talk, I'm just talking about that end of the graph in general. Not too many specific numbers, because that's when things get quite complicated. So if most of the stars in our universe fall on this side, that are small and about the size of our sun, how come the ones we see, like in Orion, are so big? And the simple answer is that the bigger they are, the brighter they are. In part, that's because they have more surface area. There's more star to be shining. Also, because they're so big, they have so much mass, the core, the very center of the star, where it does all of the burning, is under much more pressure, and that generates a lot of heat, so it shines brighter. So even though there's way fewer stars at that massive end, they're a lot more visible to us. So that's almost all the graphs I'll show you, I promise. This here is the Pleiades. They're a group of big, hot sibling stars, of which the brightest, can't actually pick them out here, I knew which ones they were at one point and I forgot, were actually known as the Seven Sisters by various historical groups, despite the fact that you only see 6 at a time. And if you have a really dark night, you don't see 7, you see 8, because the 7th and 8th stars have the same brightness. So that's a little bit odd. Funny little mystery that I don't think we've figured out, but that's for the anthropologists, not for me. But the fact that multiple groups have linked these stars as related to each other is totally on brand, because stars are never only children. They all have siblings. So calling the Pleiades sisters, regardless of how many there are, is pretty accurate. These stars formed all together somewhere around 100 million years ago. And we call these groups that stars form in clusters. And so when we see groups of stars together, that form together, they're about the same age, they're made of the same material, we can sort of say they have the same genetics, all that good stuff. And usually, as stars get older, they drift apart a little bit. They move away from home, you get some empty nester stars. These clusters, they loosen up over time. But big stars, these are the only ones that stay really, really close throughout their lives. Here's our last plot, I promise. And so here, again, at the bottom, we have star size. And on the vertical, we've got how many really, really close friends the star has. They're so close, they're not just coworkers and acquaintances, they're in a binary orbit with each other. They affect each other. So down at the bottom, we have stars that have no friends. It's just the one, and this is where the sun is, so we're actually in a good spot already. Up a little bit higher up, we have stars that have one really close friend. They're in a binary system. So Tatooine from Star Wars is a planet that's orbiting 2 suns, so we would go put that there. I don't know how big those stars are. I bet someone's done the math, but it's not me. So we're going to put that off to the side for now. And just to keep this balanced out, up on the 2 friend side, we have some stars from Star Trek. I got to read this off. This is the Wyanti system in the Yontasa sector of the Takara sector block of the Delta Quadrant. I haven't seen Star Trek, so I don't know what that means, but it sure is a long name. But we're going to put that off to the side as well. So we can have different sizes of stars, and they can have different numbers of friends. And if we put some actual data on this plot, it looks like this. And we see that bigger stars basically always have at least 1, if not 2, sometimes more than that, really close friends. And smaller stars, that's really rare. So something must be different about the way that big stars form and live their lives that means that they stay closer to each other than any other type of star. It's also worth noting that the colors on this plot are not totally arbitrary. You can think of it like when you do a campfire. The cooler parts of the fire, the ones that are good for marshmallows, those are the kind of red, maybe a little bit orange areas. And the flames, where it's hotter, are the yellowy, orangey places. And right in the middle of the star, or right in the middle of your campfire, and in your really big stars, that's where you start to get the kind of blue colors. So we think of big stars as being blue and hot, and little stars as being red and cool. It does kind of swap your hot and cold red and blues backwards, which is a little bit confusing, but astronomers do like to name things the wrong way around. So are big stars cool yet? Well, I mean, obviously they're not. I just told you that they're really hot. So, there's that. But they're the most visible stars to you and me, when we're not using telescopes, and even when we are, they're the brightest. They do really cool stuff when they die. Supernovas, black holes, neutron stars. This picture of the black hole in the center of our galaxy, that black hole wouldn't exist without massive stars. And you might also know that it's giant stars that make elements: oxygen, carbon, silicon. The things that make up our bodies were most likely formed inside really big stars. And we know that they do weird stuff. They act differently. Because they're so hot, they have weird physics going on that's different from other stars. They do that weird thing where they keep all their friends really close throughout their lifetimes. There's a lot of mysteries going on here. And where do they come from? Why do they do this? Why do we get such big stars? Why do we have stars like Betelgeuse instead of having 17 different suns? So let's start off with how stars are made in general. This is a picture of the Orion Nebula taken by the Herschel telescope in 3 different infrared wavelengths where dust is shining. Dust in the cosmic sense means elements like carbon, oxygen, hydrogen that make up particles less than a millimeter in size. What this picture doesn't show is the gas. More hydrogen, carbon monoxide, my favorite ammonia, because those shine at wavelengths that aren't captured here. You might think it's kind of weird, say the dust and gas glow when they clearly don't do that here on Earth. And they do glow in the same sense that all of us do, because this is in non-optical wavelengths. We can't see it with our eyes. And so this material, it glows because it's got a little bit of heat. At some point drifted past a hot star, got blasted with radiation, much like what happens when you go outside in the summer. And now it's cooling down. It's sending that heat off into space, and we can see it. So when we use telescopes like Herschel or Spitzer or JWST, we're kind of using the equivalent of a really, really massive thermal camera, just in space. It's a bit more complicated than that, but that's really the gist of it when we're looking at infrared. So we've got this cloud of dust and gas, or as I like to think of it, a giant dust bunny in space. And stars are formed when gravity, that's holding us down to the floor now, starts to pull that dust and gas together. This graphic here is showing multiple blobs because, as we remember, stars form in groups. We don't get just one of them at a time. And then, like making a snowball, the bigger our little clump gets, our baby star, the more stuff that it can pull in. But gravity isn't just adding stuff on top to the outside like a snowball. It's squishing down on the inside of the star, on that core. And when you take some stuff and you squish it, it heats up. If you let it expand again, it cools down. But of course, gravity isn't taking a break to let our baby star expand. It is just squeezing and squeezing and squeezing. And so as more stuff joins our dust ball, and the core gets more and more squished and it gets hotter and hotter, eventually it gets so hot that the hydrogen atoms, the little tiniest hydrogen, they get over how much they hate each other and they join together in the power of friendship to make helium. The power of friendship, also known as photons, shoots out from the core, and we now have stars. They're lighting up, they're burning, they're turning that hydrogen into helium. So that's our little 101 on stars in general, but what about specifically massive stars? So one of the differences in how high mass and low mass stars form is that big stars kind of jump the gun on burning up that hydrogen into helium. They get started on nuclear fusion before they're even done collecting all of their material. They're eating their food and filling up their plate at the same time. It's kind of messy. So that's pretty weird, because nuclear fusion, turning that hydrogen into helium, should push away all of that new material. And yet, the star is still growing. In fact, simulations show that it really should be pushing away that material. It should stop getting bigger. But the universe tells us that they definitely do, so something's wrong here. How does this work? how do these big stars grab onto so much material even as they're shoving it away? Well, one idea is that thinking about one star on its own doesn't give us the whole picture. Maybe we need to bring back that idea of groups of stars forming together, and that there's interactions there between the stars in that cluster that's having some effect on the ability of these stars to grab in new material. So we're not totally sure yet, but one thing that would probably help here is if we look at the environments where these clusters are forming. So big stars come from big nebulas. After all, you need a lot of material if you're going to make something 40 times the size of the sun. And because remember, the sun's not even that small. It's pretty regular sized. This is Monoceros R2, or MonR2 for short. It's one of the regions that I'm studying, and it's currently baking up some giant stars. And when you get nebulas and things this big, things start happening inside them. You get internal structure. So, what does some of that structure look like? We can think of the clouds that form low-mass little stars like grass. There's not much going on. It's grass. It's pretty regular. We've all seen it. And we can think of the clouds and the nebulas that form really, really big stars like trees. They're made out of the same material, but these ones are so big that there's other things going on inside. They've got branches, they've got leaves, they've got twigs, they've got trunks. And in fact, lots of these big clouds have branches too. I went back instead of forward. There we go. These branches are called filaments, and they're areas where the dust and the gas in the cloud is denser, it's closer together, it's more likely to form stars. And these filaments that you can see drawn on in red, thanks to my lovely partner, in this case, they group up in the middle in the central hub region, almost like branches coming back together to join a trunk. And along those filaments and in that hub region, that's where we get star formation. That's where all the exciting stuff happens. But these branches / filaments, they do just kind of bring more questions. It seems like, for what we know now, the material is flowing along these filaments towards the hub. So what we assume is happening is that all of the dust and gas that's traveling along these highways is going towards these hungry little pockets where baby stars are forming. But since we can only see, one point in time and we can't really check back in 10 million years, it's kind of hard to keep track of how these things change and evolve. So this is something we're not totally sure of yet. And in fact, we haven't even seen enough of these nebulas to know for sure if the material flowing along like a highway to join up in these little pockets is even something that's totally how these things work. Is this happening in all big nebulas that have these filaments? We're not sure yet. But if it is what's happening, if all of the material is coming together into the middle, that means that we're not just getting squished by gravity at the little scales where stars are forming directly. This whole thing is collapsing. And doing measurements to find out which parts of a cloud, which parts of these nebulas are collapsing or expanding or staying the way they are is a really cool piece of analysis that there's lots of research in right now. But because we need to be looking at these nebulas on the really small scales of individual stars forming and the really big scales to look at these huge branches, we need a lot of data and a lot of telescope time and some really big radio dishes to figure this out. We're also not totally sure how these branches or filaments even form in the first place. One of our theories is that they're like lots of little filaments coming together, like the threads that twist to make yarn. Another theory says they start out as these really massive highways, and then they divide up into little lanes. We still don't know. So these areas where we're forming the most massive stars are full of questions. There's so much going on that we haven't yet figured out. But structure exists on scales way larger than the inside of a nebula. This galaxy, which looks pretty messy, I'll admit, it doesn't have any nice spiral arms that we can see, though it's got some structure. It kind of looks like a shell, which is kind of cute. So some of this structure is the direct result of stars and star formation. Can you see it? Yeah, I couldn't either. But here, these bubbles that are circled, these are the sites of stars and star formation occurring. And we'll talk about how they do this in a little bit. But first, we're going to zoom in on one particular bubble. So I assume everyone's seen this picture before. I hope so. This is the obligatory famous WWST image. And so this right here is the edge of a bubble. And that blue area, that's where the bubble is, the empty space. And this orange, that's all of the dust and the gas that's being squished out of the way by the bubble getting bigger. So you've seen it before like this, I'm almost certain. But have you seen it like this? The result from a recent paper that used machine learning on the data behind the image I showed you. And all of the red stars here are the locations of likely baby stars. And we can see right at the edge of the bubble, right at the edge of the dust, there's some big clumps of those baby stars. And that's because as the bubble gets bigger, it squishes the nebula out of the way. And all the gas and dust in the nebula gets crunched up. It gets denser, and the pressure gets higher, and it starts getting squeezed by gravity, and star formation starts happening. So all of those circles in the galaxy picture that I just showed you, those are areas where we're seeing stuff like this. But this is in our galaxy, so we get to see it in a much greater detail. So where do these bubbles come from? They're creating all of this star formation. This is a protostellar outflow that unfortunately I think the projector is kind of butchering. It's okay. So when a star of any size is born, it shoots off gas at huge speeds away from itself. The material that we can see here, jetting out of the star that's in the middle, it's so small we can't see it. This material is moving at least 100 kilometers a second, pretty fast. And the size of this thing is over 1.5 light years. Protostellar outflows, proto meaning very early and stellar being star, so baby star outflows, you could think of them, are a type of what we call star formation feedback. It's the only type of feedback that's really active for all types of stars. The other ones that we'll get to really are only big stars. So when we talk about this ball of dust and gas collapsing, this is a multi-stage process. It's not super smooth and clean. When the collapse first begins, the stuff that's collapsing in, it's not all of the stuff that's going to end up being inside the star. It's just some of it. The baby star gets the rest of its material through a process called accretion. It's collapsing under gravity, and it's also grabbing stuff in from the outside nebula. And that's a simplification. But the important part is that this accretion isn't clean, it's not simple, it's extremely messy. This baby star, it's really a baby, okay? It's grabbing stuff in, but for every little bit of dust and gas that it gobbles up, it flings some out into space. And we get these outflows. Because as it's pulling it in and it's flinging it out extremely powerfully. There's a lot of energy in there. And so we get this beautiful star formation feedback. Now, feedback is one of the surprising times that astronomers have named things well. Because a lot of the words that we use, especially in physics and science, can seem kind of weird and arbitrary. But this star was only able to form because a bit of dust and gas inside of a nebula got a little bit squished. Maybe this guy was at the edge of a bubble, like in the cosmic cliffs. And when that dust squished down, it formed a star. And now that this guy is forming a star and making these outflows, there's a possibility that it is creating its own little bubble and forming another place where other stars can form. So feedback's really cool. It's really complicated to think about though, because it's all cycles. Another type of feedback is winds. You might have heard of solar winds, that our sun is blowing material towards us. That's the material that interacts with our atmosphere and sets off auroras. Like if anyone was lucky to see some last night or earlier in the summer, there were quite a few opportunities, I think. I had to change this talk. I was supposed to do this in July, so I referenced one in May, and I had to update that. So the solar wind is a tamed down version of the kind that massive stars generate. Because massive stars really just take everything we know about how stars work, crank it up past 11, 13 maybe. So the winds that come off some of these most giant stars can reach over 1,000 kilometers an hour. And there's so much material, they actually shrink significantly. They lose their own stuff because they're blowing it so hard at the environment. And so these winds don't just affect the star, but they affect the environment too. You can see the weird kind of curvy outlines in this image. And that's because the gas, the hot stuff that these stars are blowing off is eating the nebula from the inside out. On the right hand, you see those bumps in the corner. If you've seen the pictures of the pillars of creation in the Eagle Nebula, that's what those remind me of. And that's because it's the same physics at work here. This is a different area, but they're both in the situation where a giant star is eating away the inside of the nebula it lives in. So here we see yet another type of stellar feedback that's creating this kind of bubble edge where more stars can form. And now we get to what has to be the most famous type of feedback, supernovas. The most well-known type of supernova happens when a giant star dies. It runs out of fuel. And so with nothing left to burn, it can't hold itself up to fight against gravity. So the whole thing squishes down super fast. So fast that the outside layers, the very shell of the star, bounces back off of the core and explodes out into space, forming this kind of giant shell that we call a supernova remnant. This is a Hubble picture of one of those remnants from a star that died almost 2,000 years ago in another galaxy. Supernovas are really, really big explosions. When they happen, that star becomes brighter than the entire galaxy that it lives in. So when all of that gas pushes outward, it has a ton of energy, and it shoves everything else out of the way. The bubbles that we get from supernovas, we call them super bubbles. We're so good at naming things. These are much, much bigger versions of the ones that are made by jets and winds. So those can have huge effects on how stars are formed and the locations and the environments that they live in. Earlier I said that hot stars are blue and small stars are red. It's so confusing. This is a Hubble picture of a galaxy, and we can see that in the middle we have a very red glow, and all around the edge we're seeing that blue stuff. So because massive stars are so hot, even though they have more fuel to burn, they burn through it extremely quickly. The lifetimes of big stars are fractions of the lifetimes of stars like our sun. These massive stars will be born and die in less than 10 million years, which sounds like a really long time, but our sun is 4.6 billion years old, and it's only middle-aged. So these massive stars live 1,000 times shorter lives than ones like our sun. And because they die so fast, cosmically speaking, when we do see them, they must have been born really recently. We must be looking at something that just happened. So the presence of these big blue stars indicates that star formation is happening right now. This is really exciting. That tells us something about how this galaxy must have evolved. Something must have happened recently that means it's forming all of these stars. It also means that massive stars are much harder to study. There aren't as many of them, and they aren't around for very long. So thank goodness they're so bright, or we would never see them. So despite all the research that we've done and all the cool science that's already happened, we still have a lot of questions about the universe. Some of these questions are about specific objects. This star cluster has both red and blue stars in it. So some of it's old, some of it's young. I already told you that star clusters are supposed to form together, so how come there's two things in one that have different ages? Good question. We're not sure. But some of these questions are much more fundamental. They're not really as specific as looking at one specific thing and asking what happened here. My research boils down to pointing at a clump of stuff and saying, is this going to form a star or is it not? And that is a much more difficult question to answer than you think. There are just so many physical processes at play. We've talked mostly about gravity and heat, but what about angular momentum, magnetic fields, the impact of gravitational waves, neutrino pressure? There is so much science that still has to be done in both star formation and astronomy in general. And I hope that you have all learned a little bit about what we don't know and how many questions we still have to ask. Thank you.